Okay, so the first thing, I'm going to be doing these on separate notes because I think I just maybe left a little bit too little room for me to write clearly on the board. But the first one we're going to do implicitly is 2 sine x cos y equals to 1. And I'll just walk you through it, jog your memory a little bit about implicit differentiation, and then I'll let you try the next one, see if you can handle it without any lead up. So we're looking at 2 sine x cos y equals 1. And when we answer this one, I'm not sure how much you remember about implicit differentiation, but hopefully it's pretty familiar. So I'll use product rule here, and the variables agree in the first, so I don't need to record any extra derivatives. But they do not agree when I differentiate the cosine of y. That'll be the negative sine of y times the derivative of y with respect to x. And that's going to be equal to 0, the derivative constant being 0. So now what I'm going to do is I'm going to take my equation and solve for this dy by dx, and that'll be the derivative we use. So it's negative. When I move it to the other side, it'll be positive. So I get something like this when I moved it over. And now to solve for dy by dx, divide by 2, and then I'll divide by sine x sine x sine y, and that would be gone as well then. So if you think like your textbook would, the champion of algebra that your textbook is, can anybody think of something else that we might do to this? I know. It's Friday afternoon, last block. Who wants to think about calculus, eh? Okay, how about if I go like this? See it? Do you see it? What is it? Yeah, cotangent. So it would probably be written as cotangent x, cotangent y equals dy by dx. Okay, so that was a bit of a recap. I'll have you try the next one on your own and then see if you agree with my answer. I have been known to make the odd mistake occasionally. Okay, you guys, do you like the first class that hasn't laughed when I say that? Did you? Okay. Okay, so there's the natural log xy plus 5x equals 30. Give that a... Okay, so all I'm going to do this again on the other, a bigger note, so I got more room. And the question again was to differentiate natural log xy plus 5x equals 30. Let me just double check and make sure that's the one. Okay. So, any suggestions to get started? Yes?
Expand ln xy to ln x plus.
Yeah, you don't have to. It'll work out if you don't, but I think life will be a little easier if we use the log laws first. Okay. That's what I thought of. You don't have to do that. It'll still come up with the correct answer. It just may mean more algebra if you don't, because now we don't have a product rule to do, right? Anyways, so if we try to work this out, taking the derivatives, it'll be 1 over x, 1 over y, but the variables don't agree, so we have to keep the dy by dx plus 5 equals to 0. So now I have to rearrange everything. So what I could do is, let's see here, we'll keep 1 over y on this side, and that'll be dy dx equals to negative 5 minus 1 over x. And then I got to multiply everybody up by y. So dy by dx equals negative 5y minus y over x. So yeah, we could leave it at that. We don't need to do any more with it. I think if you were to leave those together, a common denominator would get us 5xy minus y. I think that's what people in first block ended up with if you kept the xy together. It's the same thing, it's just one's a common denominator, one's not. Okay. So let's just see, how are we doing? Hands up if this was, you could do the implicit differentiation. Okay, so maybe we need to spend a little more time there. We have one more we'll try together, and that's finding the slope of an implicit graph. So we're pretty good at finding derivatives, and remember, you always got to keep in mind you're finding a rate of change. You're also finding the slope for a tangent line. So for implicit functions like this crazy looking x cubed plus, or x plus y cubed equals x cubed plus y cubed, that's a relation there. There would be a picture for the graph. I'll see if I can dig it up for you. We should be able to find the tangent line there. So let's see, what will the slope of the tangent line be at -1 and 1? Okay, let's try working this one out together then. So the question was x plus y cubed equals x cubed plus y cubed. And if we differentiate implicitly, it's going to be a chain rule question here. So 3x plus y all squared. But then I have to times by the derivative of the inside. So that'll be times 1 plus dy dx. And on the other side, I'll have 3x squared plus 3y squared dy dx. And now I got to try to isolate those dy by dx's. So the pieces here, x plus y squared let's see here. Can move these to one side. So let's move them all over to the left side. I'd have 3x plus y squared dy dx. Take away 3y squared dy dx equals 3x squared minus 3x plus y squared. And now I can factor out and solve. So if I factored out, I'd have dy by dx and 3x plus y squared minus 3y squared. So I can divide then and end up with the implicit derivative. So then I'll get dy by dx is 3x squared minus 3x plus y squared all over 3x plus y squared minus 3y squared. So I can see a few things that we may want to try in order to help clean it up a little bit. For example, everybody has a 3, so we could factor that out. And I look at all those, they look very similar. There may be some simplifying, so I'm going to expand it just to see if it cleans itself up. I don't know, to be honest, if it will at this point, but you know how much we like doing algebra, so why not give it a shot. 2xy and minus y squared. And then down here it would be x squared plus 2xy plus y squared minus y squared. So let's see what cleans up. And again, I don't know if maybe I've gone too far, but let's see what ends up here. So that's going to be, so I'm left with negative 2xy minus y squared. And on the bottom, I'd be left with x squared plus 2xy. So yeah, I'm not sure that that's tidied it up any better. We could factor out an x and a y there too, but I don't think it's going to get any better. So we'll cut our losses there. We'll say I think that's about as far as we take it. This we were asked to find at the point, is it -1, 1, or was it 1, -1?
-1.
This one? Okay. So in order to figure out what that's going to be then in the equation, that means I need to substitute for x and y. So -2 times -1 times 1 minus 1 squared. And on the bottom it'll be -1 squared plus 2 times -1 times 1. So 2 minus 1 over 1 plus, no, sorry, 1 minus 2. So I get 1 over negative 1. So it gives me a slope of negative 1. Okay, so the last topic, which you may have forgotten a little bit about from implicit differentiation, was using logs to help you remove chain rules and things. Now I'll tell you, I expect you to know the log differentiation technique, but it's not going to always say use log differentiation like it does here. You'll probably have to look at the question and go, oh yeah, that looks terrible to do. I'll bet you I could do this with log differentiation, right? There's a square root, which means I have a chain rule and a quotient rule, and there'll be some other chain rules inside of this. It kind of looks like it needs to be simplified somehow, and that's what we're going to do to get started here. Is before we deal with y equals to the root of x squared minus 2 over x squared plus 2, we're going to log both sides. And then we'll use as many of the log laws as we can to help that get us out of these product and chain rules. So I could take the square root out. And I can also use the division rule, which says I could subtract the logs. So, not sure if I'm going to run out of space here, but that's the natural log of x squared minus 2 minus 1/2. Yep. Okay. Next line. That was correct. I just ran out of room. 1/2 natural log x squared minus 2 minus 1/2 natural log x squared plus 2. Okay. So, what we can do here is now we just have regular, we can't really cut this down anymore, but we've removed the chain rule and the quotient rule. So life is better now. I mean, it's not good because you have to do calculus, right? But it's better than it was before you had chain rule and quotient rule. But we do this implicitly. That's going to be 1 over y times the derivative of y with respect to x. And then I take the derivatives on this side. That'll be 1/2 1 over x squared minus 2 times 2x. There's a chain rule in this, don't forget. And again, for this piece, that'll be 1/2 1 over x squared minus 2 times 2x. Sorry, that was a plus 2 that time. Okay, and then I just tidy up what I can. So that 2 and that half would be gone. That 2 and that half would be gone. And 1 over y dy dx is, let's see here, 1 over x squared minus 2 minus 1 over x squared plus 2. So,
X over.
oh yes, thank you, I forgot. Getting too excited, I guess. Right, so I forgot these x's right here and here. So now to solve for dy by dx, all I got to do is I'm going to take this y and move it up to the other side across the equals. So I'll get dy dx equals y times x over x squared minus 2 minus x over x squared plus 2. So, happy there? There's one more thing to do. Does anybody remember? Yeah, we had an explicit equation up here. That's an equation defined in terms of just x. So we should give an explicit answer down here. It says that y is equal to the square root of x squared minus 2 over x squared plus 2. So we can add that into the derivative here. We can say then that dy by dx is the square root of x squared minus 2 over x squared plus 2 and x over. So now we have a derivative that's entirely in terms of x, just like when we started with the function in terms of x. Okay. So yes, the derivative looks monstrous, yeah, but it was because of the substitution we did there. And I do think that if you were to try this in the alternate way, that you'd see this is actually better. The next topic we did was inverse derivatives. So there was two things in the inverse that we had to think about, or sort of like a two-step process. Does anybody kind of describe what that relationship was like? Or anybody kind of remember? Maybe give me a, maybe you don't know the whole thing, but you kind of remember parts of it. Remember loosely how is an inverse connected to its the function's derivative? Yes? Yeah, it's the reciprocal. So the two slopes are reciprocals. But remember what we said you had to do was you start on a point and you find the corresponding point on the function or its inverse. Right? So first we have to flip those coordinates around to figure out where that corresponding point is. And then the the derivatives are reciprocals. Okay, so I'll show you what the I never memorized this myself. I always remember this little identity that if I put an inverse inside the function, I get back to x. And the reason this is helpful, I don't have to memorize this rule. If I differentiate both sides, I'll get chain rule here. So that's the derivative of the outside times the derivative of the inside. And then I can solve to figure out what is the inverse derivative. It's the inverse derivative equals 1 over f prime of the inverse at x. Okay. So let's walk through an example. You do need to, just to be clear, this is an identity, this is a formula here that you may be expected to work in an example. Like you might have information like a problem and you're told that, you know, this value is 2 and f prime of 2 equals 5. What's the inverse derivative, right? You still need to know that relationship. That's particularly something that the Barron's book would be fond of asking. You know, like they don't want to give you a full function. They don't want to give you the picture. They just give you some numbers to see if you understand how to use them. Yeah, but this identity here, I don't memorize it. I just find it from that identity that we talked about way back in Math 12. Okay, so now let's try using these just so you kind of get an idea again for how we did those inverse derivatives. Okay, so the first one, it says find the value for the inverse if f of x equals cosine 2x. And this is where I'm looking for it. So basically I'm looking for the inverse derivative at 1/2. Okay. So step number 1, we don't know what the two reciprocal slopes are until we find the location of those slopes. I know one of the locations, but I don't know where the other one is. So the first thing we have to do is find that corresponding point. Okay? If this is the x value in the inverse, what do you know about it for its function? It's it. It's the y value. Yeah. So what I'm trying to figure out then is, first, if I want to know where is this point, I have to find out where does the cosine of 2x equal 1/2. So to do that, I have to go back to my trig equations. Doesn't Math 12 feel so great now that you've been subject to calculus? You're just itching to get back there, I bet, huh? Okay, so you might have forgotten how this goes. My suggestion was that you make a substitution. You don't have to do it this way if you found another one. I'd be curious to hear how you did it. Let theta equal 2x. And remember, we had to keep track of the bounds here. So from 0 is less than or equal to x is less than or equal to pi over 2. And if that's true, then x is theta over 2. So I can make a replacement here. and I can find out that now my bounds go from 0, well, we'd have to multiply by 2, so now they go from 0 to pi. Okay. Maybe hopefully it's jogging your memory a bit. It's been about a month or two since we've talked about this. To solve this equation, it's going to be in this triangle. This is 60 degrees. This is 30 degrees. So the cosine is going to be this angle. So cosine will have a reference angle of 60 degrees, or in our world, that's pi over 3. And it's a positive number, so cosine is positive in those two quadrants. But this one here is out of bounds, so there is only one answer, and it's pi over 3. So if theta equals pi over 3, we can use that and figure out the value for x. That means x is pi over 6. Okay. So now what I know is the point on the function, the point that corresponds to it, is the point pi over 6, 1/2. So it's not always going to be as involved as solving a trig equation, but the first step is always the same. If you're given a point on the inverse, you have to figure out where that point corresponds on the function. So now I have that corresponding point. I now have to find its derivative. That derivative is the reciprocal of the one I'm looking for. So the derivative is going to be, it's cosine 2x that I'm using. So it's going to be the negative sine of 2x and times 2, because this is a chain rule question. So it'll be negative 2 sine 2x. And at this particular value, pi over 6, so 2 times pi over 6, that's pi over 3. So if I look at that same triangle up here, the sine of pi over 3 will be root 3 over 2. So it would be negative root 3. So the steps we did were find the corresponding point. We've now found the corresponding derivative. It's the reciprocal of this for my answer. Okay, so this would be, like if you're on Who Wants to Be a Millionaire and this is your question, you'd say, yes, Regis, my final answer is 1 over negative root 3. You probably deserve to win $1 million though, right? If you could answer that question? Okay. The other thing was we introduced a set of other inverse functions that you needed to know, like the arc sine, the arc cosine, arc tangent. Hands up if you forgot them already. Okay, fair enough. Yeah, just in case you're wondering again, remember there are no formula sheets in our course. If you're wondering what have I forgotten, it's all listed here on this inside cover. Okay, so this is what you'll be expected to know. In all practical purposes, most of you should be happy if you know the arc sine, arc cosine, arc tangent. If you know all 6 of them, that's fantastic, right? But the most common ones, of course, are the sine, cosine, tangent. No guarantees, but they are the most common. So let's try one here. E to the x arc sine x squared. Yeah. Okay, hands up if you remember arc sine's derivative. Right, you're not near. I remember it, so you're cool like me if you remember it. Okay, it sounds like some of you know it, so give it a try and then we'll see how you did. Okay, I'll do this one on a fresh sheet.
Yeah, but u is x squared, so x squared is x to the 4th.
Oh yeah.
Okay, so let's walk through this. This is a product rule question. There's 2 functions, and there's a multiplication in there. So to take its derivative, it's going to be the derivative of the first, which everybody loves. Plus, this time we do the derivative for the second. So the derivative for arc sine, normally it's going to be 1 over square root 1 minus x squared. But this is now an x squared, so there's a chain rule in here that's going to pop up. So this is going to become 1 over 1 minus x squared, all squared, times the derivative of the inside, which is 2x. Okay, I believe the way your textbook presents it to you is it presents it as u prime over square root 1 minus u squared.
So we got that anyways.
So your textbook is basically giving you it in chain rule form. That's what it is. It's sort of like in the chain rule form, this is what it looks like. Okay. So if I try to tidy this up just a little bit, it would be e to the x, arc sine x squared, plus 2x e to the x over 1 minus x to the 4. Okay.
Oh no. Why must rates be related?
That is, yeah, I mean, we might be able to simplify a bit, but let's not go there. Let's move on, shall we? So the next question is one from your related rates homework. So I imagine some of you were able to do this. Some of you maybe had some troubles. So amongst yourselves, see if, maybe you're familiar with the problem. See if you can work this one out. Okay, and have a discussion. You can chat a couple of neighbors over. Maybe someone there knows how to help you. And we'll get back together here. We'll review. Okay, so why don't we see whereabouts we're at. So we always should have a good picture to help us figure out the things that we're looking for here. So that's an okay picture of a tank, I guess. And we're going to put the information to the problem into this tank so that we know this depth is 12 feet. And we know that it's 10 feet across the whole thing. So 1/2 of it will be 5. And it says water is flowing. So let's try this again. At 10 cubic feet per minute. So we would label that as the change in volume with respect to time is 10. It's increasing the volume at a rate of 10 cubic feet per minute. And it wants to know about when the water is 8 feet deep. So this is approximately what my picture would look like. And we have to ask ourselves here, okay, when we look at this, we've got a few things in this problem. We've got a volume, because we're talking about the water increasing. We also have this radius and this height that we have to figure out how they're related. So it's nice that there's a formula for this. Pi r squared h over 3 is the volume for a conical tank, or a cone. Now, one problem that we've got with the way the information's been presented is if we look at this, there's two variables here, r and h. Okay. One question that was asked by the other class was, how do you know if you have if it should be included, right? Like, how do you know that it's volume, radius, and height? One thing you have to ask is what things are changing and what things are constant. All the things that are changing should be a variable. So this is changing, this radius, this height is changing, so is the volume, so they all need to be included. If by some miracle the radius never changed and it was a constant, we may not need to put it into this problem. But anyways, if it's changing and you can see it's going to be a length that's growing or a speed that's increasing, it has to have a variable in the problem. Okay, but the issue here is all we've been asked about is the depth of the water. So that's how fast it's creeping up like this. Which means what I'm looking for is what is the change in the height with respect to time. Okay? So if I want to find the change in height with respect to time, and I know this about the volume, the problem is I know nothing about how the radius is changing. If you were to go on and start doing this derivative, somewhere in that derivative you'd need to have a dr dt. But that's the problem. We don't know what dr dt is. It's not been information given to us. So because we don't have dr dt, we have to try and find a way to get rid of the radius in this problem. So the way that we do it is with similar figures. So it's these two triangles here, this big triangle, which is green, And let's go purple. This triangle here, which is also a similar figure, we can write up a little equation that would say 5 is to 12 as r is to h. Okay? And if I solve this for the radius, 5h over 12 is the radius. That way I can substitute this piece in for the radius, and now I only have a problem with h, which is okay because that's what I want. I'm looking for the change in height, so h is a good thing to keep in your problem. So we're going to make an adjustment then. The volume will be pi. For the radius squared, it's now 5 over 12h. So that'll be 25 over 144, which means once I tidy this up, 432, I believe you'll get this for the volume, 25 pi over 432 h cubed. And this is the one I'm going to take the derivative implicitly with respect to time. So dv dt is equal to 25 pi over 432 times 3h squared dh dt. And this is the piece that I'm going to try to solve for. So let's rewrite if we solved it for dh dt. So dv dt, I'm going to move the 432 up and the 25 pi, and there's a 3h squared coming down. So that's been rearranged so that I now have dh dt. And it tells me in the problem that h equals 8 feet at that instant, and I know the change in volume is 10. So I can put everything in, and it'll give me 10 for dv dt times 432 over 25 pi times 3 times 8 squared. And with a little bit of help from the calculator, we can then tell you how fast that water is rising. Okay, so let's see here. 10 times 432 divided by 25 pi. Ah, shoot. Okay, hang on. Thank you. Yes. Okay, so we get 0.286 roughly. 0.286. And I believe these units are in feet per minute, I think. Let's just see here. Feet and minutes. Yes, so it is rising at a 0.28 feet per minute at that instant. Pardon me? I am recording. It will be on YouTube. Okay. Do people need a minute to copy this down, or can I advance this a little? Hands up if you need a minute. Okay. Okay, so one more related rates question. Hauling in a dinghy. There's two parts to this. The first one, we're going to look at the speed as the boat approaches the dock. The second one, we're going to look at the speed as that angle is closed in while the boat's being pulled in. Okay, so again, I'm going to let you guys try to set up the problem and do what you can with it, and then I'll show you my solutions in a minute. So, if we look at this question and we put in some of the information, I'll call this R for rope. At that particular instant, I know that the rope is 10 feet, and it tells me that the boat here is moving towards the dock at 2 feet per, or sorry, the rope is being hauled in at 2 feet per second. So that means as the person standing here that says ahoy is pulling the rope in, they're pulling it in dr dt. Okay, what's the rate of change here? 2, is it? Are you sure? Why might it not be 2? Ah, why would it be negative 2? Why? Why might it be negative 2?
Because your point is getting shorter.
It's getting shorter. That r is shrinking, so that should be a negative 2. So you may have some different, you may ended up with, a positive or negative extra in your answer if you didn't incorporate that. Now we have to figure out how to relate the things in the problem. What I'm interested in is this speed here. I would like to find, why don't we call it, well, let's call it A since we're in part A up here. So what I'd like to find is the change in A with respect to time. Now I got to figure out how to relate these pieces together. So we'll assume that the tide hasn't changed, so that the boat is 6 feet. That's constant, right? That problem would become a lot more complicated if we put the tide into it. But we could say that r squared equals a squared plus 36, and that's how we could connect those things together. So to take their derivatives, 2r dr dt, almost the funniest derivative ever. Anybody seen that Simpsons episode? No. R dr r? That was the... Okay, anyways, never mind.
Yeah, Mr.
Barnett said exactly the same.
Oh, did he?
Yesterday.
That's funny. And we didn't even talk beforehand. Okay, so this is the derivative we end up with. We're going to solve it for dA dt. So the 2's will divide out. And r over a dr dt is dA dt. So I can fill these values in. It says that there's 10 feet of rope, and dr dt is negative 2. And we can use Pythagoras up here, this relationship, to figure out the value of a. So a equals the square root of 100 minus 36. That's square root 64, which of course is 8. So that'll be negative 10 over 4. Yeah, I think, what was yeah, we could also shrink it one more. Negative 5 over 2, which is negative 2.5. So, okay, so now this time we're going to take a look at part B, which wants to know about the angle. So, how did you, anybody have a suggestion on how we're going to relate these things together this time? Tangent? Okay, so tangent means we're going to have opposite and adjacent. That'll work because we already know if we're going to use A, we need to know what the change in A is, and we found that. So yes, that will work. I'm going to work this question as though you didn't have all this prerequisite knowledge, because it could have just as easily been one question that said find the change in the angle. So let's pretend that we go all the way back and we don't know any of this extra information. Okay? How do we figure out how to relate them? How could we do it so we don't have to use the stuff we just figured out? Yeah, cosine this time. And again, you do have the right answer. You could use sine, tangent, or cosine because we found that extra piece right here. But anyway, if we just go all the way back and try to work it from the beginning, this would say cosine theta is adjacent over the hypotenuse. And we would use this to figure out the rate of change. So that'll be negative sine theta d theta dt. And you probably want to think of this as 6r to the negative 1. So that means, using the power rule, it'll look like this. And we have a dr dt in there as well. Okay. So if I solve this for the change in the angle, which is right there, I would get d theta dt equals, let's see here, so the negative signs would disappear, and I would get 6 and a sine theta down here, and dr dt here. So, let me see, did I do that I think I've done that properly. So the only thing I don't know in this situation is I don't know what the value of theta is. So I'm going to have to figure it out using the values 10 and 6. I could even do one more thing. If I know that this side is 8, because we could find that using Pythagoras, the sine of theta is going to be 8 over 10, or 0.8. So then I could replace the sine of theta with 0.8. And what are we moving at again for the rope? Or sorry, the rope is 10 feet long. So it would be 10 to the negative 2. And we're moving at negative 2 feet per second. So we would end up with, let's see here, 6 over 80 times 2. So we'll just make the whole thing negative 12. And again, it should make sense that it's negative because that angle is going to be shrinking. Sorry, I'm just going to have to steal that for a second. So with the calculator, negative 12 over 80 is about 0.15. So negative 0.15 radians per second. So let's take a look here then at Newton's method. This is kind of question that you might see appear if this was a test question in multiple choice. Because if the question simply asked you to solve for 2x squared minus 3 equals 0, you could just use the 0 method on your calculator. But where this one, because the initial guess is given, if you follow the same method, meaning we all do Newton's method, we'll all end up with the same answer. So to use Newton's method, we need the derivative. And that means I'm going to have 1 minus my first evaluation with Newton's method, using 1 as my initial guess, would look like this. And let me see here. I believe that's, let's see here, was it 1? That'll be 4 minus 1. 3 is 1. So 2 minus 3 is 1. So it should be 1 1/4, I believe. Okay. And then we do it again. This is 1 first iteration. We'd go 1.25 minus 2 times 1.25 squared minus 3 over 4 times 1.25. And this time I believe we would get 1.225. So this is the second iteration. That's the answer that we'd be looking for. It is not necessarily the answer, but it shows me that you can follow Newton's method, because we should all end up with 1.225 if we all use Newton's method with the initial guess of 1. Okay, so it's not enough to just use the calculator to solve it. You do need to know how to use Newton's method. I want to see that you can do it. Okay, so the last thing I want you to try with Newton's method is see if you can solve for the intersection of those two curves. See if you remember how that goes.
So x squared minus goes next to 0.
Yeah, yeah.
Minus 1 or x? X.
What's n? You start off with this, and you plug 1 into here, and then get an answer. You plug this into there, and get an answer. Plug this into
So there's two answers, I believe. We'll find the positive one. If you put this into your graphing calculator the way I had asked you to be shown, is you will use y1 for the function and y2 for the derivative. And we'd put it in the TI-83 like this. And then we keep going, except the next time we use the answer as the value for x. And the nice part about it is once we get to this step here, we can just keep hitting the equals key. Yeah, everybody's aware of that, right? You just keep hitting equals again? Okay. And then I believe, does anybody have an answer on this one? It's like a 0.824. Okay, so let's go, that's enough then if we go 0.824.
What is that? X.
That means when I looked at the picture, this is about what the picture looked like, and the -1 and 1 were here. So I guessed it was a half. That's the first value it used to start looking for a solution. You could have guessed a quarter. You could have guessed the only ones which would be bad guesses. It would be a bad guess over here at 0 because you wouldn't find an answer. But you know, closer the better.
And